Good afternoon, everybody, and welcome to this exciting webinar where we're looking at IDEA StatiCa as a design link for Prokon SUMO. My name is Jacobus Oberholster. I'm an AEC and Prokon technical consultant with Micrographics, and you'll also check my email address there in the bottom left. And of course, you are more than welcome to contact me after the webinar if you have any queries or you're actually interested in a personalized demo. We'd be more than happy to do that for you. And let's not dilly-dally around any longer, and let's get straight into our agenda for today's webinar. So for today, we'll look at a quick introduction. We'll look at understanding SUMO design links. We'll look at exporting our SUMO model to IDEA StatiCa Checkbot. We'll look at navigating Checkbot and opening a connection. We'll look at modeling a connection and designing that very connection. We'll look at how to group connections. And then lastly, we'll end off with a conclusion. So just as, in a sense, a heads up that I'm doing everything in real time, just so that you can see exactly how the process works. And unfortunately, that might mean that here and there we'll have a bit of, will require a bit of waiting, just as we proceed through the webinar, just looking at the different content from using Checkbot, etc. But so with the Prokon IDEA StatiCa design link, it is something very, very new. It was released just before Prokon's version 5.3 was released, but it's now being made official through Prokon version 5.3. All right, so you can see over there, we are working with Prokon 5.3. There's been some really cool updates to a lot of these different modules, and I would recommend that if you haven't taken a look at just some of the content out there on what's new in Prokon 5.3, I'd really recommend giving that a go. So what we're going to do is we can go to our analysis tab in SUMO, and I'm sure that many of you are familiar with Prokon SUMO module. We'll go to File, and we'll go to our SUMO model. All right, so this is a very basic, just a support frame. I'm just going to turn some of my load cases off just so we can see the frame itself. All right, so this is a very basic support frame just to demonstrate the functionality that's been added to your design workflow with IDEA StatiCa. We can see we've got our braces there. We've got some bracing beams. We've got our main beams and our columns and so forth. And then if we have enough time, of course, we'll look at some of our base plate connections with the braces as well. But again, if we don't get to that in this webinar, you are welcome to reach out to me, even if it's to say, hey, can you please create a YouTube clip on something like this? It might already exist, and I'll just forward you that link. Otherwise, I'll be more than happy to actually create some additional content. There's also something I forgot to mention is that we do have a live chat. And of course, throughout the webinar, you are welcome to ask questions. I'll keep an eye on the live chat and I'll do my best to answer your questions. If I can't answer your question, I'll probably ask you to reach out to me via email, and then we'll attend to your query like that. But all right, we've got a very basic model here. And just one of the things that we'll see with IDEA StatiCa is that we can now design our connections in 3D, actually taking into consideration members coming in from all angles. And although in most cases these connections would be seen as quite simple, if you take even a connection here, you can actually model the main beam with its stiffening beam coming in and those braces as well as one connection in a sense. So you can actually check the full load effect on at that nodal point, which is really very, very cool. But all right, what I'm going to do is I'm just going to run my analysis. We are running a second order analysis type, and that's just because we have these lateral forces coming in on the model as well. So I'm going to just run the solver quickly, and then we'll just look at design links before we proceed with our IDEA StatiCa design link. So, all right, an important thing that we distinguish between is analysis and design as actually core terms or principal terms. And so SUMO is predominantly an analysis package. And what that means is that in our results workspace, we actually look at our our load effects. So that would be your axial forces, that would be your torsional forces, and so forth. Let me just change that, multiply a bit, and X moments, Y moments, etc. And those forces, or the magnitude of those forces, do not tell us whether or not a specific member or connection passes. All right, so that's analysis. And although most of us would probably argue that displacement in itself is can be used as a design check, absolutely. But predominantly we see this, or we see Sumo as an analysis package with some design functionality. But then from there, we go to our design links, and this is where we now proceed with our design of different elements um, in our model. So we look at combine as something that we do for the members. We have base plate and so forth. We've got our columns, pad footings, etc. And then we actually physically go and design those elements according to some international code. All right, so your analysis is analysis, right? So you'll have a bending moment in China is a bending moment in South America, is a bending moment in Greenland, is a bending moment in South Africa. But design is done in accordance with a specific set of national codes, or in some cases, as we'll see now, we'll do that according to the Eurocode, which can be tailor-fit to a specific country using national annexes. But so just to look at our the common design links that we have available, I'll just select this model. I'll go to combine. I'm not going to take any of my load combinations with. And what this will do is it'll export the geometry from Sumo as well as the load effects. All right, so we see a nice wireframe model there. I'm going to tick that it's braced in both directions. I'm going to say evaluate current sections because, of course, that's the first thing we want to do. Is we just want to make sure that all of our members pass their checks. What's really, really nice is that if you name your elements or your members or your profile groups within Sumo, it actually pulls those through. And that means that you know exactly what you are checking, which is really very, very nice. I really appreciate that change. It used to be like that with Frame, just as a given. And I believe that that functionality has now been extended with using the combined design link from Sumo as well. And we can see a nice little legend there as well. And as we select them, it actually underlines that little legend over there. Right, so I'm just going to select stiffening beam, beam and column. I'm not going to do the braces. I'm going to click on add, go to design, and just go for list all failing members just to run a quick check. And we see we actually have some members that fail, and we'll have to go through those and see exactly why they fail and so forth. All right, so that is the generic design links that we're used to. And of course, then you can make use of the design groups as well. And those basically take a couple of these design links and just expand on their functionality, especially the combined design group functionality. It's really very cool because you can actually check your members and update them within Sumo, which is really very cool. And I do have some content on that as well that I'd recommend you check out. But right, that's not what we're here for. We are here for the IDEA StatiCa design link. All right, so this is unfortunately with a little bit of the waiting is going to begin, but I'm just going to select my entire model, go to design, click on IDEA StatiCa, and the loading screen is now opening up on my other screen, which unfortunately I can't show you, but I assure you that the Checkbot loading screen is there. And what it's now doing is it's pulling information into Checkbot, and here we go. All right, so this is the start of everything where you can see your project folder. The project folder is usually, or is by default, the same folder that your Sumo model's in. All right, so that's where it will create that project folder. You have two different project types, so steel and concrete, and then we currently have these design codes to select from, with of course the Euro codes also being applicable within the South African context. Hopefully, if IDEA StatiCa gains significant traction within the South African market, we might even see our South African codes loaded or added to the list of available design codes. So thumbs up. Let's hope that we gain significant traction for that. But all right, this is the basic setup. So there's nothing more to it. This is how we start. And then what we do is we click on create project. And this is the checkbot interface. And we'll see here, there are no items in the project. First, select nodes and members in the linked model, and then choose to import other connections or members. Okay, so that basically just means that your entire model has to be selected within SUMO, which it is. And then what you do is you either click on import connections or members, depending on what you're looking to make use of, whether it's IDEA StatiCa connection or IDEA StatiCa member. And I'm actually doing a webinar, I think it's in 2 months' time, on designing a castellated beam in torsion using IDEA StatiCa member. So please look out for that one as well. But what we're interested in is we're interested in the connections. So I'm going to click on import connections. You see now what it's doing. It's pulling all of that information from SUMO into Checkbot. We might have to do some mapping, but if we've done the mapping before, we don't have to do that. So the mapping is that you're just telling it, this is the member convention within SUMO. This is what that member is. All right. So you choose from quite a big range of available catalogs. Now, even though this was the second last point, so that is the point on the agenda was how to group connections. What we already see here, and this is with the latest update of IDEA StatiCa, the functionality was there in IDEA StatiCa 24, but they've improved it significantly with IDEA StatiCa 25. And what you'll see is, depending on the connecting geometry, you'll see that there are groups. And if I select a particular connection, so you see there's C226 and C62. If I select C62, okay, let me just deselect everything. I select C62, you can see that it's grouped with C226, and it actually highlights that little connection block, which means that the geometry is identical, even though it's facing maybe in different directions. And you can see once you've done the modeling and design for a specific connection as a part of that group, you can select the group and say calculate all. And then what it will do is it'll use that geometry that you've assigned to a specific connection and check the other connections load effects with that specific geometry. So you don't have to go and design every single connection. You'll just make use of that calculate all functionality, which is really cool. If you want to design individual connections, you don't want to group them, you can always explode a group. So what we're going to look at here is we're going to look at C62, and we're going to pull that into IDEA StatiCa connection. So I'm going to click on C62 and I'm going to click on open. So what it's doing now is it's pulling the geometry as well as the load effects that are already visible in IDEA StatiCa Checkbot, or that's already loaded into IDEA StatiCa Checkbot. It's pulling that into IDEA StatiCa connection, which again is unfortunately just opening up on the left-hand screen. So here we go, and we can see here, this is pretty much exactly what it looks like in our analytical model. And now we start the process of actually setting this up, creating this connection as it would actually look in real life. That's really, really nice. So the first thing I'll do, I'm just going to set my column as the bearing member. And then even though you can't adjust these members, you can see everything is pretty much locked. You can rename them to simplify the process, to simplify the process for yourself. So I'm going to click on M55. I'm going to right click and I'm going to rename this to column. Okay, so it's quite important for me that I know that this is the column, and you'll see when we start assigning our operations why it is helpful to rename your members. Now, importantly, because we're working through Checkbot, so I'm just going to go back to Checkbot again, these elements take on the orientation of the members within SUMO. So it means that within SUMO, you have to ensure that your member orientation is correct. All right, so very important that you actually, it's now, if you want to make use of the design link, it's important to care, or important to pay attention to the orientation of your members. So say, for instance, if you want this member to be horizontal, so basically with the web being horizontal in IDEA StatiCa, through the use of the design link, you actually have to rotate it within your Sumo model and then proceed with the process. Okay, once you've pulled this through into Checkbot, it is pretty much locked in. If you make changes, you can always go to Checkbot and you can synchronize the model again. All right, but just so that you know, once you're in connection, that orientation is fixed and you have to synchronize the model again and rerun this connection so that the member orientation is updated. Okay, so I've renamed my member. I'm not too concerned with renaming the others, but you can name it beam 1, beam 2, beam 3, stiffening beam, main beam, etc. Whatever works for you. Then I want to take a quick look at our load effects. Now, this is where I found that people can get quite confused in that load effects are not the same as imposed loads. So in Sumo, these line loads are imposed loads, but they generate the load effects, right? So the load effects are your axial forces, your bending moments, and so forth. And that's really where the checkbot functionality is really powerful, in that it pulls those load effects through for you. And can you imagine now, considering the different directions, etc., if you had to go and balance out these forces? Now, because they are all around the same node, they have to be balanced. There's a slight imbalance here, but it's not going to throw us out. But the brilliant thing is that you don't have to go populate this table manually, which can really be just a schlep if you think of the different conventions for whether or not a bending moment is rotating clockwise or anti-clockwise and so forth. So really, really cool. I think that is really that's really the thing that sells Checkbot for me, is these load effects. All right, we're happy with everything. And what we're going to start doing now is we're going to start building up our model. And that's done through operations. So I'm going to click on operation. The first operation I'm going to go for is the cut operation. And that's to actually extend my column. All right, so even though it's called cut, which in itself is maybe a bit counterintuitive, we use cut to extend the column so that we can connect these two beams within plates to the column. So I'm going to go to member, select column. It's going to be cut by M60. Bounding box is good. I'm going to tick extend member, and the direction I'm going to change to perpendicular so that it doesn't weld those members together. And I'm going to set the offset to minus 250. We can see it's just short there. So I'm going to make it minus 300. Okay, so that makes sense, of course. We're not going to model like this in Sumo because we're working with just a purely analytical model within Sumo, whereas here we're looking at modeling the connection exactly as it would be in real life. All right, so with that done, I can start my end plate operations. So I'm going to do one for M51. It's going to connect to column, and we can see it creates a nice default end plate there. We of course want to modify this. We're not quite happy with the way this looks. And you can see there's quite a lot of information here. There's a lot that you can change. So I'm going to do this. Sorry, that should be positive 25. And I'm going to do positive 25 on all edges. Right, so I'm quite happy with that. I'm going to increase the size of my weld to 6 mils. And then I'm going to change the orientation of the bolts. Now, this can be a bit of a painful process, but what I would always recommend is looking at these dimensions, because these dimensions can actually guide you a bit. You can see there's 30, 30, 30, 30, and we see those 30s over there. So I'm going to go for my top layer. I'm going to go minus 50. Let's see what happens. And we see that it moves it down. So it takes a bit of getting used to, and the convention could be slightly different for different operations. I'm going to go minus 50, minus 50, and I'm going to see if I can maybe go for a second one. Let's go for minus 100, and I want this to be nice in the middle, so let's go minus 80, and we see it's 80 aside, and we've got 6 bolts, so 3 on a side. Okay, so I'm quite happy with that. That works quite well for me. What I'll do now is I am going to copy this, and apply this to the other side by just changing the member 1 to M30. And there we go. All right, so that's quite easy. Those are my end plates. I'm quite happy with that. This M60 might give me a little bit of a problem just as we're connecting to the web of the column, but I did set this up so that it is a torsionally pinned connection. So if we go back to Sumo, we're looking at this connection here. If I click on this member here, you can see that it's torsionally fixed, which technically means it is pinned on either side, but it's not free to rotate around its own longitudinal axis, which is something I see people get wrong relatively often. If you want to use pinned in this case, because we're working in 3D, it means that actually this member is free to rotate around its own or about its own longitudinal axis, which causes an instability in the model. Right, so unless it's a brace that you'll only expect to see axial forces in, you have to use the torsion or the torsion fixed, sure, why am I a bit lost for words? The torsion fixed fixities on either end for your model to be stable. All right, just a bit of food for thought. Food for thought, that's the word. All right, so just some insight there as to why if you're setting its fixities to pinned, you can actually have some problems. All right, let's get back to this. So we now have to connect member M60 to the column and go for operation. And I'm just going to go for a shear plate, so which we know as a fin plate. I'll set M60 as the member, and it should be connected to the column. Right. So that is basically that. So we can actually simulate this connection now. It will most likely fail. All right, but when it fails, that's where we'll really see IDEA StatiCa connection stand out and really as an incredibly cost-effective solution, especially where our standard connections fail. And in practice, we might because we don't have that functionality usually available to us, we might feel forced to actually upsize a member, whereas that might not be necessary. All right, so I'm going to click on calculate, and it's now going to start this process. Okay, that's all good. So it's running. All right, so it's running through all of these load effects. So what connection does is it looks at the worst case of all of these load effects and then uses that to perform the analysis. All right, so even though when you look at load effects, the program will identify where those load effects came from and what the load combination was that generated those effects, connection does not work with pure load combinations. If you have multiple load effects, so C1, C2, C3, it will take the worst case load effects out of all of those, and that is what it will use to analyze the model. So actually a really, really nice way to check connections, but it does mean that your analysis time is slightly longer than what you would expect under normal circumstances, because you can see as it's running through multiple iterations, it's trying to create the worst case scenario. All right, so we see a massive failure here, absolutely massive failure. And what IDEA StatiCa connection does, or specifically in accordance with the Eurocode, is that the failure limit is actually based on the plastic strain and not the yield of the material. So in this case, it fails if the plastic strain reaches 5%, which means that we can slightly exceed the yield, the yield strength of the material itself. Right, so I know that there are engineers that will sort of limit themselves to 1.5% plastic strain, and that you can actually set up that the program stops at 1.5% plastic strain, or you can even set it to 0%, which means that the yield strength of the material will be the failing criteria. All right, but we're sitting at 1,366.7% plastic strain, which is absolutely horrifying. And what we would then normally do is we would go back, we might make some minor adjustments to the size of our end plates or the thickness of our fin plate, etc. But in general, under these circumstances, we would go back and we would increase the size of these members, even though this member itself might be passing all of its checks with flying colors, right? So if the actual utilization of this member was maybe 50%, but now because of this connection, we have to upsize that member, and that can be incredibly expensive because this member could be quite large, right? It's a 5-meter column or whatever it might be. We might find ourselves in a position where upsizing the member is really an expensive approach. IDEA StatiCa allows us to actually experiment with the use of stiffeners, stiffening plates, ribs, you name it. Right, so the first thing I'm going to do is actually put a cap plate on this column. So let's take note that plastic strain is sitting at 1,366.7%. And I'm just going to add a stiffening plate to the top, or a stiffener to the top of the column, and we're going to rerun our analysis. So I'm saying not specified, and this is going to be, well, center is fine, and go for end. We'll see there is that plate. I'm going to put just my welds on the inside, and I'm going to increase the size to half of this plate thing. So it's a 14 mil thick plate, but that in itself, just even the manufacturing process, which you can do with laser cutting, and the installation will be significantly cheaper than upsizing a member. So I do not expect that we're going to win with doing this, but we will note hopefully we'll note a significant improvement in the plastic strain percentage. Of course, there's a lot of other stuff we can do. And what I really like about IDEA StatiCa Connection is that we can actually check some modifications, and we can check that those modifications actually have zero effect on the performance of this connection, which means that we'll also not waste money by adding plates and stiffeners that have no effect on the actual model's performance, which is really, really nice. It really is something that can lead to incredible cost savings. And that is something in South Africa that we really need to get behind. I think we're not quite there yet where we care about just saving on material costs, because we're consultants in a sense. So for us, what wins the client over is our consulting fees, and it really needs to get to a place where we're actually going to improve on actual the amount of material that we use and save our clients money there. So we might be more expensive, but we're saving our client probably hundreds of thousands of millions of rands on optimizing our material use. You can see that with just the addition of that plate, we've actually gone less than half of what our previous plastic strain was. And you can see that's just adding a 14 mil stiffening plate. All right, so this entire member is giving us problems. And what we're going to do is we are now going to start with maybe increasing the thickness of some of our end plates, increasing our bolt sizes. So that's an important one. So I'm going to increase my bolt size. Let's maybe go for M20s. Let's see how they perform. They're nice and big. And I'm going to do the same on EP1 as well. Again, you can rename these. Right. So if you find this a bit confusing, you can always go and rename them. I'm going to add some stiffeners to the back here as well. So I'm going to go for operation, stiffener, and column, and not specified. Yeah, so that should be fine. Let's see what it does. Yeah, that should actually be okay, just as it is. Just giving me a bit of beans here. I think if we go for the front. Okay, I'm going to restart this one shortly. What I want to do before then is let's add a cleat to the bottom here. I'm going to go for M60 bottom flange, and it's going to be connected to the column. You can see there, and location is going to be rear. So that's right at the bottom there. We need to adjust the spacing a bit. It actually is going to give us some problems if we don't adjust the spacing. So I'm going to go for a bigger angle. So this is what this interface looks like. I'm selecting members. Let's go for a 150 by 150 by 18. Ooh, that is very thick actually, but we can always come back and modify our connection that it's a bit more economical. Let's see what happens if we adjust the transverse position. All right, so that's quite okay. I'm going to do that as 30. And this actually looks okay. If we look at where these are positioned at the moment, so I'm not going to worry too much about them. And let's run our analysis again and check how much we've gained on our plastic strain. And again, you can imagine that just with the modifications I've made now, that this is not something that you would be able to do in your standard software packages. You might be able to create maybe some stiffening webs using plain shells and those sort of things, but actually you wouldn't be able to check it in such detail. So let's just hang 10 for this guy to finish just running through all of his load effects. And again, we'll note the plastic strain. I think this might actually bring us to a place where we might need to upsize our members potentially, but hopefully we can get away with not having to do that. I do doubt it. I must admit, I'm not optimistic looking at where our plastic strain is sitting at the moment, but we can bring it down significantly by actually using the different operations we have available to ourselves. So we're almost there. We're almost at 100%. And then we should hopefully see some good improvement in our plastic strain. Okay, so we're there. Let's have a look. Okay, so we brought it down to 462. I think what I'll do as a last effort is just see if I can add those plates at the back here, and then I'll go back to Sumo, change the size of our members, and we'll run through the synchronization process just so that you can see what that looks like. So I'm hoping that's going to work. I might have a bit of a problem doing that. For some reason, it is giving me a bit of beans when I try to do that. Let's have a quick look. Okay, column. Okay, and then we'll do location is front. All right, so that's right there. Okay, let's see if that improves. If that improves it significantly. So we'll do this once more. I think we're not going to win that much more out of just modifying this connection to the nth degree. At some point, we also have to realize that, okay, cool, now we really do have to upsize our member. Wow, look at that, down to 38%. That was quite significant, actually. So I'm hoping, let's see if we can actually win this now. I'm quite optimistic. I didn't think we'd win that much. I'm going to increase this weld size to half the plate thickness. If we look at our end plates, I think this is all okay. I'm going to increase this size slightly. So let's go for 18 and 18. I'm going to increase the size of the shear plate or fin plate as well, or the thickness. I'm going to go for 15 here and increase its bolt size. Okay, let's see. Let's hope we can kick this thing in the face. As I say, you can see it's actually running a lot quicker now, which is very nice. I think because of that massive plastic strain, the program takes a bit of strain actually, and maybe now it is just running a bit quicker because it sees that stiffening effect actually helps it a lot to run through its analysis. 16.1, we are almost there. Okay, our column is still taking a bit of strain. Let's see. Okay, these bolts are also taking some strain on this side. So I'm going to go and let's see if M24s will work. I'm hoping they're going to fit in actually. Let's see what side. Okay, that still looks okay. We might have some issues with edge distances. So I'm going to go for M24s. That's all good. And I'm going to see about actually adding another stiffener at the bottom here. All right, so let's go for stiffener. I'm going to go for column. And I am going to go for position is just lower. Location is rear. Sorry, that should be front. And let's see about adjusting its X position. So let's see 150. Okay, and that actually looks quite good. Let's see what happens. I'm maybe going to increase the size of these guys by a mil. Oh, let's hope we can do it. Let's hope we can do it. What might limit us in practice is we're wondering how on earth are we going to install these. That is not our problem right now. But you can see that actually through the modeling process, you can see those kind of things beforehand and actually see that, oh, for a guy to install these will be actually quite difficult. Oh, we're at 5.1. Come on, we need to do this. I'm not giving up. Let's go increase the size of those welds. Right, so the flange weld actually, or the web weld can actually be made a bit smaller. These guys are going to be made a bit bigger. This stiffening plate up there, okay, that's all good. Oh man, I really hope we can do this. Let's increase these to 16. And I'm going to increase this guy to 16 as well. Let's go for it. Come on. Come on. We need point something down. Come on. Less than 5%. Right. Okay. There we go. Look, I will be honest with you. I'd have to think really hard about whether I want a connection like this. But again, if this is a 5 meter, 8 meter high column and up, you can actually do the maths here in terms of what the fabrication cost of all these stiffeners would be versus upsizing your column. And that really is where IDEA StatiCa shines. Even in the webinar that I'm going to host on using IDEA StatiCa Member, it actually allows you to model in stiffening plates for your flanges, which can make a massive effect, and they are cheaper than upsizing a member. So IDEA StatiCa shines under these circumstances, and we shouldn't limit the applicability of IDEA StatiCa to just complex connections, but actually connections of any complexity where we can work through this process and actually not exhaust all our options, but really look at what options we have available and what we can do. And that we can save significantly with just the fact that we can model in all these different modifications and see what effect they have on the model. So we can see what we have is we have a weld failing on this side. I'm going to increase that weld there for both. So I'm going to go to 7 on both sides for the flanges. Okay, there's 7 on the other side as well. That's great. And I'm going to run the calculation one more time, and then everything should pass. Now, again, some guys will not come. Some engineers will go like 5% is or 4.7 is just way too risky to sit at that percentage of plastic strain, and we'd look for 2%, 1.5%, whatever it might be. But the reality is we could actually get so far that we pass. Whereas our first, if you remember, our first plastic strain value was at 1,366.7%. And we got it down just through the process of changing the size of bolts, changing end plate thicknesses, changing weld sizes, and modeling in stiffening plates. We actually got it down to 4.7%, which is phenomenal. Honestly, I was not that optimistic that we would get that value, but really amazing. And we can actually start seeing some dead zones in a sense, and we can actually now work through the process of slowly adjusting the thickness. Let's say we're looking at this stiffener and we're going to bring this down. Let's bring it down to 10%, 10 mils, and see what happens. All right, so I'm going to just run the calculation one more time. If it fails, I'll just bump it up again, and then we'll start going through our checks and our reports. And you can see there that, okay, it seems like this stiffener now has very little effect on this model passing. And what I'll do then is I'd remove, I'm going to delete the stiffener. I'm going to run my calculation again, and let's see. And what's interesting to note is you can actually see the effect of stiffening up different parts of your connection, how that works in. Oh, look at that. How that works in to actually, as you stiffen up different points, that actually start taking away stress from less stiff elements, or less, yeah, elements that aren't as stiff. Okay, so I'm going to go back to undo. I'm going to reduce this guy maybe to even 5 mils. Okay, let's see. Okay, I might even reduce that guy even further. But so I hope that this principle is now clear, that one, for you as an engineer, you can actually see how stiffening up different parts of the model will take loads or stresses away from other parts, which makes sense. Because usually what we work with is we're actually working with stiffnesses, right? We're trying to make different parts stiffer so that they pull more of the loads towards themselves. Okay, so we see we actually need a little plate there. We might be able to get away with making it like 5 mils thick. And even here, what I'd start doing is I'd start modifying the thickness of these plates, slowly reducing them. And you can see once the model is nice and stiff, that the analysis actually runs quite quickly. All right, so from here, we can now go to our check tab. You can also take this connection. So, sorry, let me just go back here. You can publish this to a connection library, which is a massive online connection library, which you can actually go and look at for free. And you can publish this to a company library, which only the people that have been loaded onto your company's IDEA StatiCa license can have access to. Isn't that brilliant? So you can actually go publish these connections to a company library, and people in the company can access those templates and make use of them, which I think is really, really cool. All right, so I'm going to go to check. And here, what we can do is we can actually cycle through different displays. So I'm going to go to equivalent stress. And again, there's yield. And you can see that the legend does not exceed the yield value of the material. And that again is because our failure criteria is actually plastic strain and not the yield strength of the material. But what we can see is we can actually identify hotspots in the model where, I mean, you can even have a plate welded on. You can even check what effect that would have. But we can see throughout our model what are the hotspots, which is really, really helpful so that you know where to go and make modifications. Now, I would say that if the plastic strain is in hundreds or thousands, honestly, I would make some modifications I would actually add some stiffness and stuff to my model and get it to maybe below 50% first before I start looking at this. But then from here, you can actually come look at the equivalent stress, look where the hotspots are, so that you can modify the correct members, the correct plates, and so forth. Or we can look at plastic strain as well. We can see where are those hotspots, and we can see that the failure is up here. And we know that, okay, so these end plates are really important. And what I might do is actually extend this end plate a bit upwards as well. Maybe push the beam a little bit more downwards so that I can put another set of bolts at the top here. Maybe look at something like that. And that maybe would mean that I can get rid of some of these stiffening plates to save a bit more money. We can look at our stress and contacts. We can look at our bolt forces. Now, this is something that you would maybe remember. The display looks quite similar to what you would expect in Prokon's baseplate module. We could then look at our mesh, and this mesh can actually be modified. So you don't have to, if you feel like the mesh is too coarse, you can go to your settings and modify this mesh size. And then lastly, I'm just going to reduce this. We can look at the deformed shape of your model. I can increase this. Oh, there we go. No, I don't want something that high. Or maybe want to look at 10 or 5. And we can see what is causing these problems. Very, very interesting. All right. Then you can go through these different tabs here where you look at plates. Now, of course, everything passes here, so there's nothing that will be highlighted for us per se. But if specific plates are failing, you'll actually see it here, and you can identify that plate and go back and reinforce it. You could look at your bolts. Again, here, actually, everything is passing, I think even all our detailing checks, which is really, really nice. Now, the detailing checks work according to the restrictions in the code, where it says that when you're welding onto this specific plate, the weld cannot be smaller than that, or it cannot be bigger than that, etc., etc. The detailing checks don't necessarily make the model fail, but they do get highlighted as something that you need to pay attention to. Now with bolts, you can click on this plus, and what you'll start seeing is actually a series of calculations, which is really cool. And then the same for your welds as well. So you can actually look at them, look at their throat thicknesses, their length, and so forth, which is really nice. You can actually see there's a detailing warning there. So what I'll do is if I expand this, I'll actually find some information on that. So you can see the detailing check. It says the weld is too small. Throat thickness should be greater or equal to 10.1 millimeters, where rupture of the weld is to be avoided for ductility purposes. And it actually gives you the code reference as well. And you can go and look at that. So really very nice. Again, doesn't make the connection fail, but it's something to pay attention to. And that will be listed in your report. So from here, we go to our report, and this is something that we need to generate. Okay, so we have different project item settings here. So this is relevant to the report. We can also tick theoretical background and software info. I'm going to tick a couple of these, and I'm going to click on generate report. Now this is generating a design report for us, which is really, really comprehensive, quite a big document. You can set this up that it summarizes this data. You see that's such a cool picture of our connection. And here you'll see just an absolute, a massive amount of data. Quite like this. Like, just imagine providing somebody with a report like this. It's so flippin' cool. So I really like it. And what we'll get further down, so these are all of our calculations and checks. Further down, we'll actually get a bill of materials. So let's go further down. Again, I've really selected for a maximum amount of information to be displayed. Again, this can be narrow summarized better. You can see there's a cost estimation. These are in euros, but you can set them up at the in rands as long as you have a unit cost per kilogram. Okay, so that's something that maybe you'd know. If you had to convert bolts like M24s to a unit cost per kilogram, that can be done. That can be done. You know what the weight is. Well, actually, this would come down to the length of the bolt as well. But you'd be able to give yourself an estimated value per kilogram, and then it can generate a cost there for you. Same with your weld, same with the plates, and so forth. And we start entering the bill of materials, where it lists out all the plates. And from here, you'll see there's some additional information here. So theoretical background, so CB film, etc., etc. And then from here, you can print this as a MS Word file, as a PDF, or DXF. And what that does, if you send it to DXF, it actually puts all of your plates in a DXF with their thicknesses, which you can then send to the fabricators to actually laser cut for you, or depending on the thickness, maybe use water jet cutting or flame torch cutting and so forth. So really, really cool. You can see a type of report. We can go to brief. We can generate. You'll see here something much shorter. Okay, this is just the project data and your checks, the summary of your checks. You can go to a one-pager. All of this on one page, which I don't think it can do. To be honest, that's a very long page, right? And so forth. Okay, another cool thing is you can save this file and you can open it in the online viewer, where you can export it as a 3D DWG, which you can then import into Inventor. and actually do all of your detailing there. So it actually creates individual parts of this entire connection, and I do have some extra content on that as well. All right, so we've saved this. I just want to go. I want to give this maybe a name. I want to call this principal beam connection. It's number one. This can be in accordance with a grid line. It's very nice, like A1, B1, etc. The author is myself. All right. And the description will be main beam connection in model with worst case load effects. Okay, and then further you can assign some project notes and so forth. So I'm going to say save. Should be able to close this, go to Checkbot, and you can see that for C62, there is the connection, and there's all of its checks. Of course, we haven't run a buckling check, but we can do that as well. And you can actually see that that's now been recorded in Checkbot. And it's actually, you can see now the box has got a different color, meaning that it has been done. So again, if I click, you can see the little tick mark. If I click there, I can see that connection. So now I'm going to click on the group. I'm going to click on calculate all, and let's see what happens. Okay, come on. I think it is actually doing that check. I'm just not seeing anything. Okay, there we go. You can see the little loading button there. So it's actually running that check. And we'll see what it does. Okay, it's checking C62 again. Just making sure. Let's just give that a moment. But what it's saying for us so far is that what we've done for C62 works for C226, and we can actually use that connection on both sides. Okay, so that's done, and it runs through. You can see here that our plastic strain is actually at 0.2, and both of them have now been checked. I think that's absolutely epic. And you can see for some of these, like for group 5, there's 3, for group 3, there's 4, etc. But it's checked both of those for us, although what I would have liked is just a picture of that connection over here as well. But that's not the end of the world, and that's maybe something they're going to do in the future. I really hope so. So right, that's it for just the content for this specific webinar. If you have any questions, you're welcome to ask. I'll hang around for a minute or so, but then again, you are welcome to reach out to me directly using my email address for any further information, for a personalized demo, whatever it might be. You're really welcome to get hold of me. And yes, thank you for even dropping by. I really hope you've enjoyed this. If you haven't already, please subscribe to our channel so that you get these notifications. And please, if you liked it, you're welcome to hit the like button, and also just put something in the comment section. We really appreciate that. I always love seeing just a bit of interaction on the content that we put on YouTube. It's just nice to know that people are looking at it, they're enjoying it, they have questions. It really is, it's reassuring that what we're putting out there is really helpful for you as users and potential users of the software. So yeah, that's it from me. I'll hang around a little bit. But other than that, again, thank you for checking in. I hope that you have an awesome afternoon further, and I look forward to seeing you in our future webinars.